as requested by Bhaskar, we will do a few questions based on the interaction of electric dipole in a non-uniform electric field and also dipole-dipole interaction. Okay. But before that, I want to start with a couple of questions which I've selected for you. So we'll start with something based in mechanics. So this example next, like this. We have an open tank with liquid inside it. It's a water. And we have something like a wooden block. It is tied to a rope. It's kept at the bottom like this. So this is a wooden block of mass, let us say 2 kg. Now in this situation, when the tank is at rest, the tension in the, so this is a light thread. The tension in the thread, say T0, appears to be let us say 8 newtons. And we'll take G as 10 meters per second square. And density of water as usual as 1 gram per cc. Now next what happens is that the whole tank and this situation is given a horizontal acceleration. Tank system with the block tied inside it is given a uniform horizontal acceleration of E equal to 7.5 meters per second square. So draw a diagram to show the orientation if the block is at rest with respect to the moving tank. Okay. And find the angle of inclination of the thread with respect to the vertical. And the tension in the thread. So just try out this question. We'll start with this. So this is going to be about your application of non-inertial frames, pseudo forces, buoyancy, free body diagram, all these kind of concepts. Not yet got the correct answer. So I'm just making two figures and you tell me which one is the correct orientation, okay, when it is given acceleration. So one case I'm saying that if given acceleration like this, then the orientation should become like this. Okay, this is case A. And another case I'm telling that if it is given acceleration like this, the orientation will actually become like this. Which of these two are correct, A or B? Uh, no, no, Chakshu, that is in fact the wrong answer. And I'll explain in a moment why that's the case. No, in fact, so basically this is the correct orientation. This is the wrong orientation. Now I'll explain why that happens. So let me draw this in more detail. So what happens is if the system is given a horizontal acceleration like this, the surface of liquid itself will become inclined like this. So the pseudo force acting backwards. No doubt about that. Okay. But at the same time, this will become oriented like this, such that this line will be perpendicular to the surface. And I'll show you why that happens exactly also. In terms of free body diagram. So what will happen is that ये जो एंगल है वो exactly इस एंगल के बराबर होगा. So that this is mutually perpendicular. And I'll explain why that happens, because if you look at an XY frame attached to the tank, it becomes a non-inertial frame. It's traveling with an acceleration like this. In that frame, what is happening? The pressure gradient is like this, minus rho A because of pseudo force. Okay. So now you think in terms of free body diagram of that object, and you will understand the horizontal pressure gradient की वजह से buoyant force is not acting only vertically now. There is also a horizontal component of buoyant force. Understood? So there is going to be pseudo force which acts on the block along with weight, but there is also going to be a horizontal component of buoyant force along with the vertical component of buoyant force. Have you understood this point, people? Okay, I hope this point is clear, people. Horizontal pressure gradient concept. So you know this thing, right? That there is this kind of pressure gradient in an accelerated tank. In a horizontally accelerated tank. Okay. If you make a free body diagram of a fluid element, you understand why that happens. In the frame of the tank. So on that fluid element, there is pseudo force and there is weight. So there is like this, and there is force due to pressure like this. So this diagram actually shows you that horizontal pressure gradient is minus rho e if the acceleration is along the x-axis, and vertical pressure gradient is minus rho g if y-axis is anti-gravity, like this. So because of that, the surface is inclined like this. Tan theta becomes del y by del x or e by g. Okay. So this kind of thing. So now when we apply that to the free body diagram of the block, you will immediately understand that for the wooden block underwater in this non-inertial frame is accelerating like this with the tank with our xy axis selected like this. So the wooden block with respect to this frame is in equilibrium. Okay, so forces should balance. But what are the forces acting? So there is pseudo force, but there is also buoyant force ka horizontal component. There is mg, but there is also buoyant force ka vertical component, and there is tension acting something like this. Okay. So buoyant force is horizontal component will become density of water into volume of the block into E. Buoyant force is vertical component will be density of water into volume into G. Okay. And just like in comparison, mg is density of wood into V into G, and me is density of wood into volume into E, pseudo force. Okay. So now this free body diagram is actually very easy to solve. You can see that if you take the vector sum of mg plus ma, you take the vector sum of ma and mg, that is like an effective weight, which is m of the root of e square plus g square, like an mg prime. It's like the apparent weight inside the non-inertial frame. And likewise, when you consider the buoyant force ka x component and buoyant force ka y component, you will see that they lie along the same line but in opposite directions. It will become like the effective buoyant force, which is okay. So that will be density of wood, density of water into volume into root of a square plus g square. Okay. So that is why this angle will be equal to this angle. Okay. but then this force will be more than this. Okay, the effective buoyant force will be greater than the apparent weight, and that's where now tension comes in. So tension will balance the difference. Okay. So that theta will be tan inverse A by G. So this is the easy way of solving it without getting into too much of vector analysis. But for that, you have to understand that the ratio of Vx and Vy is the same as the ratio of pseudo force and gravity or weight. Is this concept clear, people? So this is the free body diagram in that non-inertial framework. Okay, good. Okay. So just work out the final answer. It's pretty easy. So you realize that what happens is when the tank is at rest, at that point of time, tension is equal to buoyant force minus mg. Okay. Whereas when the tank is accelerated, like this, that time tension becomes effective buoyant force minus apparent weight, like this. Okay. So you can see here that this tension was 8 newtons, mg was 20 newtons. So buoyant force was equal to 28 newtons. So that means density of water was 28 by 20 times density of wood. Okay. So here the effective buoyant force, okay, will be density of water minus density of wood times the volume into root of a square plus g square. Okay. Whereas here this was equal to density of water minus density of wood into v into g. So if you just divide these two equations, you'll understand. So T prime by T will be nothing but root of a square plus g square divided by g, or like the effective gravity divided by g. So in this case, this is root of 7.5 whole square plus 10 square divided by 10. So you're taking the acceleration to be 7.5 meters per second. Okay. So the tension will get altered by a factor of 5 by 4. You can take 2.5 common here, 3 square plus 4 square. So that's 5 by 4. Okay. So the new tension will become heat into 5 by 4. So it will become 10 newtons. Okay. Because the effective weight would have changed from 20 newtons to 5 by 4 times 20 newtons. It would have changed to 25 newtons. And the buoyant force would have changed from 28 newtons to 5 by 4 times 28. So that is 35 newtons. Okay. And that theta would be tan inverse E by G. So in this case, it would be 37 degrees. So this is the complete solution of this. Okay, so the tension changes to 10 newtons and the angle of inclination becomes like this. What are people clear about this? Yes, people, hope this is clear to all of you. Finished with this? Okay. Let's move on to my next question. Now, this is based on concept of impulse and variable mass a little bit. Okay. So the next example is this one. We have a chain which is dropped from this vertical position at t equal to 0. So chain of mass m, length L, held vertically with one end just touching the floor is dropped at t equal to 0. So we have to find the normal contact force N at an instant when the top end has displaced through y downwards. Assume the chain does not heap on the floor. Okay. And the links do not bounce on impact. That is, they make inelastic kind of impact. So by telling you that it's inelastic impact, I've actually given you part of the hint in the question. So you have to basically find this normal contact force as a function of y, where y is the vertical displacement. Okay, so by the time the chain has become like this, that this end is displaced by y. So this vertical part is L minus y. Okay, so at that point of time, what is the normal reaction due to the flow? That is what we have to calculate. Let's try out this question. Yes, Chakshu, your answer is correct. Okay, good. So here you have to understand a couple of things. One is that from this position, when the speed of the chain was zero, okay, till this position where certain portion of the chain is on the ground. So this is y, this is L minus y. So what has happened here is that this is now having a speed v. So what will that speed be? So that speed will actually be root 2 g y. Okay. And this will not come by energy conservation. Mechanical energy is not conserved. Okay. Rather, there is free fall through a displacement of y. So two things you'll understand, that if you look at the free body diagram of any link of the chain as it is falling, single link, while it is falling down, okay, it has only one force acting on it. There's only mg acting on it. So its acceleration will be equal to g. And the falling links are not in contact with each other. That's one thing to understand. And the second thing to understand is that mechanical energy is not conserved, because as a link hits the floor, okay, there is dissipation of energy, because there is non-conservative, a non-conservative inelastic collision impulse. So that's another important thing to understand conceptually, that mechanical energy is continuously getting dissipated in this problem. Okay. So that's why the free fall velocity is V. Okay. Now to understand the normal reaction, what you have to understand is that if you think of the part of the, this is the section Y on the floor. So this is a variable mass system. Okay. So we have to understand that the net force acting on it is equal to rate of change of its momentum. We can't just write it as mass into acceleration because mass is not constant. So at time t equal to t, its mass is, let's say, m prime, which is m by L into y, and its length on the floor is y. Whereas this part, it's falling with a velocity v. So what happens at an instant of time dt later, a mass dm over here, which was falling with v, becomes part of this. So at time t plus dt, its mass has increased to m by L into y plus dy. Okay. Or it has become m prime plus dm. Now the dm mass has got added to it because its effective length has increased by dy. Yes, Omkar, your answer is correct. Okay. So between this instant and this instant, when we look at the forces acting on this section, there is normal reaction and its weight. So net impulse, that is n minus m prime g dt. This is the net impulse in the upward direction will become equal to how much? The change in momentum in the upward direction, which will be dm into v. Because that particle dm coming down, its momentum changes to 0. So that is why you will see that the normal reaction is equal to dm by dt into v plus m prime. So it is equal to m by L into v plus mg y by L. Why? Because dm is equal to m by L dy. So dm by dt is equal to m by L dy by dt. So that is m by L into v. So this is applied. So the normal reaction becomes the linear mass density into v square plus mg y by L. And further, you know, v as a function of y is root 2 gy. So that's why your normal reaction's instantaneous value is 3 mg. Okay. So it's like normal reaction is equal to the weight of the portion y on the floor, okay, plus force due to collision impulse or impact force kind of. And as it turns out, this part is equal to mg y by L, and this part is your lambda v square, which is effectively how much? It is 2 times mg y by L. Okay. So you can see that your collision impulse is actually double of the weight of the portion which is on the floor at any point of time. It's double of the weight of the portion which is on the floor. Okay. And another thing you can be asked in a question like this is that the energy dissipated by the impact forces or the inelastic collision impulses, which you can calculate by work energy. So you can see over here that the delta E, you can say, is equal to change in kinetic energy plus change in gravitational potential energy. So if you were to calculate this, you would see this is a negative quantity, and this is the energy dissipated due to inelastic impact. And this can of course also be calculated. So this was one type of question I wanted to discuss. Alright, so effectively the answer comes out to be this imprint 3 times. Alright, so that was this question. Now next, we're going to discuss one of the questions which have been asked as a doubt also. So we have this case of the two rings which are moving in opposite directions. Such that the center to center distance is something. So X, these are metallic rings of radius r each, and they have lambda as the resistance per unit length. The material. Now this whole situation is inside a uniform magnetic field going into the plane. So you have to find the current in each of the sections of the wire. Okay. So if we label this point as, let's say, this point as H. So we have to find the instantaneous current in this section FGECD, and the instantaneous current in the section DHF or the section DEF, like this. Okay. So, you people familiar with this question? Have you solved this recently or still a doubt? Okay, solved recently. So then shall I move on from this question? Still a doubt, okay. Okay, so I'll briefly describe the two methods by which you can solve this. Okay, and then those who haven't got it yet, you can try it, and if you have difficulty, you can get back to me. So method one we can apply is the motion generated EMF concept. So you can use motion generated EMF, which is the easiest way of solving this. So in that, what is happening is that So what you do is, for example, this section that we are taking, so first just consider this thing. Just consider this thing moving like this. So this acts like a combination of, so this moving inside a magnetic field like this. Let's say the magnetic field is B naught. Okay. So this acts like a cell like this and some resistance like this. So this section actually acts like this. So this is some E1 and there's some R1. So E1 will be how much? It will be B naught into some L effective into V. Okay. Now what will that L effective be? This will be the L effective. Okay. So if you know the center to center distance, you can find L effective in terms of X, where X is the center to center distance. Okay. And R1 of course will be lambda into arc length EF ABC. Okay. So this is also going to be some kind of function of X ultimately, which you can calculate. Okay. So do that. Okay. Now similarly, this section, suppose this is G or whatever, this section which is moving, CGE, this also becomes the same sort of battery. Okay, because it's moving like this. Okay. But some different resistance. Oh, sorry, it's moving in the opposite direction. So this one is moving like this. So it will become battery ka polarity ulta ho jayega. So this section will be moving in this direction. So V cross B is downwards. So this will be a battery, let's say E2, but its magnitude will be E1, the polarity, and this resistance is something else. Okay. So this will also be V naught into L effective, into V, where L effective is the same length, CE. Okay. And like that, this section on the other side, which is moving like this will act like a battery like this. Okay. And some resistance. And finally, this section over here, this one, this is moving like this, so this will also act like a battery and some resistance like this. So ultimately, this whole thing can be reduced to an effective circuit. Okay, so this whole thing can be reduced to an effective circuit where this arc over here is replaced with this sort of a thing, R1E. Okay. Then this portion is replaced with cell like this, different distance. This portion is again a cell like this, resistance same as this side, and finally this portion like this, resistance R1. So this is what your effective circuit becomes. So each of those EMFs is equal to B naught L effective into B, where this is the L effective. This one here is your L effective. Okay. And R1 and R2 are basically the smaller arc length and the larger arc length into lambda. So is this the method you people have used while solving it? Chakshu, is this the method you use for solving? Okay, good. So this is one method. Okay. So Ananya and Bhaskar, have you understood this, Omkar? Will you be able to solve this from this method now? Okay, very good. Okay. Now the other method you can use is also, you can use this thing, Faraday's law. Okay, so you can also use rate of change of flux method. So in that, for example, you can consider the smaller loop or you can consider the larger loop, whichever you like, and you can see how its area is changing. For example, one time you can consider this whole larger loop, okay, and see how its area is changing. dA by dt will be a negative quantity, so the flux going into the plane is decreasing, so that should create clockwise current in this. So that will show you the current in this outer loop. Let's say it's I1 was out there. And another time you can consider this area, let's say there's this one, d prime. So that dA prime by dt is a positive quantity. That area is increasing. So flux into the plane is increasing, so there will be some anti-clockwise current. So there will be some I2 type of current here in this one. Okay. And to consider the flux, how it is changing, how the area is changing, you can consider something like this. It's basically just geometry. So if this is where the overlap is at some point of time, then you will see that that original A that was there for the large loop, okay, it is basically twice of this area. This area is A, let's say, that was twice of A. और ये हम बहुत आसानी से निकाल सकते हैं. कैसे निकाल सकते हैं? In terms of this angle theta, we can calculate it very easily. So this area, this shaded portions area, will be the area minus the area of this section. So this section's area is the area of this whole thing minus the area of this triangle. Okay. So this whole thing's area will be how much? 2 theta upon 2 pi into pi r square minus the area of the triangle. So the area of the triangle is, okay, so this is, let's say, A prime. So this A is equal to pi r square minus A prime. Okay. So that A prime is this thing, the area of the whole sector, which is 2 theta upon 2 pi into pi r square minus the area of the triangle. The area of the triangle will become half into base, which is r cos theta, into height, which is 2r sin theta. Okay. So that is, you take r square common, so we get theta over here. You get theta over here minus यहाँ पे कितना आ जाएगा? Sin theta cos theta, or sin 2 theta by 2, something like this. Okay. So this is the same thing here. Like this. So the large area is double of this, and the small area is just double of this. So you use that over there. And then when you are calculating dA by dt, for dA by dt or dA prime by dt, use the relation between x and theta. So again, you will see that this was x and this angle was theta. Okay. So x is equal to 2r cos theta. So dx by dt is becoming minus 2r sin theta d theta by dt. And dx by dt is equal to minus 2v, because that's the rate at which x is decreasing. X is the center to center. So dx by dt is the relative velocity of approach of the two centers. So it is minus 2. Okay. So from this, use this as a constraint relation when you substitute this. Okay. So you will get the areas as a function of theta. Differentiate that, and in that there will be a d theta by dt term. So that d theta by dt term will be eliminated from this. So is this method clear, people? So I'm just leaving this like this on the whiteboard notes, so you can go through it later and understand it by this method also. So this is also a very interesting method of solving this problem. Okay. Now, since we are on the subject of this, I want to discuss a couple of more problems based on EMI. Okay. So next is based on a very old subjective JEE problem actually. So in this, the x-axis is drawn like this, the y-axis is drawn like this, okay. And gravity is like this. Okay. So a non-uniform magnetic field given by the relation V is equal to V naught 1 plus y by L k cap exists in the region shown. Okay. And now what we're doing is we are taking a rectangular frame like this, rectangular metallic frame. So rectangular metallic frame of dimension L by 2m, mass m, and resistance per unit length lambda is released from rest in the vertical xy plane as shown. Okay. So now what we have to do here is, first of all, find its acceleration and induced current I at an instant when when its velocity is v downwards, okay, in terms of v. Okay. Also indicate the sense of induced current I. And secondly, find its terminal velocity after a very long time. So assume that it doesn't impact any ground below anything. So the motion just continues indefinitely for a very long period of time. So in that case, what is the terminal velocity after a sufficiently long time? So just try out this example. Okay, let me verify the answers. So first of all here, you have to understand one thing, that because our x-axis is like this and y-axis is like this, z-axis is into the plane. So the magnetic field that we've written, which was B naught 1 plus y by L k cap. So those magnetic field lines will be looking like this, going into the plane, and the density of the magnetic field lines is increasing as you go down because the y coordinate is increasing. So ऐसा कुछ है. So it's something like this. So at some instant when this is having a downward velocity v, okay, so you can see that the flux going into the plane is increasing. So it should create a current anti-clockwise like this. Okay. So that is something you have to be very careful about. Your right-handed Cartesian system, you have to understand that x cross y is j going into the plane. So k cap here is into the plane because I cap is like this and j cap is like this. So there will be in fact an anti-clockwise current in the loop PQRS. Now the easiest way to calculate that current is going to be by using motion generated EMF. So we can see that in terms of motion generated EMF, this section is going down. So V cross B is going to act like a battery like this. Going to act like a battery like this, let's say. And this section is going to act like a battery like this, let's say. E2. And of course, there is some net resistance of the loop. That's, let's say, R. So R is equal to lambda into perimeter, which is 6m. Now even now at some point of time, if this has a y coordinate y1 and this has a y coordinate y2. So in this diagram, you can see that in this situation, you can see that your E1 will be B1L B, because obviously this length is L and this length is 2L. So with those dimensions in mind, you can see where V1 is the magnetic field at the y coordinate y1. So it is y1 by L. So that's your E1. And likewise your E2 will be B2LV, which will become B naught. Just move this thing. So, okay. So this will be 1 plus y2 by L. L into B. Okay. So this current I will become E2 minus E1 upon R. So it will become V naught LV into Y2 minus Y1 by L divided by 6 lambda R. Okay. Now you can see that Y2 minus Y1 is 2L. So this will become V naught LV by 3 times lambda L. Sorry, this is L in the denominator, not R. Or 2 by 6, we convert that. So it will become V naught V by 3 lambda. This will be the current. So is this the answer you people were getting? Just check my calculation. Should be correct. Okay, so 2 V naught LV divided by the effective resistance, which will become 4 plus 2 is 6 lambda. So it seems correct. Okay. So this is the instantaneous current. Okay. And you understood the reason why it will be anti-clockwise. Because unusually here the z-axis is into the plane, not coming out of the plane. So now that we have got the current, we actually have to go in the reverse direction. We have to first find the current, which we did, and from that we will find the magnetic force, and from that we will find the acceleration. So next thing we'll understand is the free body diagram. So as this loop is having this anti-clockwise current inside magnetic field which is going into the plane, which is increasing in strength as you go down. So this is y equal to y2. So magnetic field V2 here is 1 plus y2 by L, and this is y equal to y1. Okay. So magnetic field V1 is equal to V naught 1 plus y1 by L. Okay. So from this you can also see that V2 minus V1 is equal to y2 minus y1 by L V naught. So V2 is effectively equal to twice of, 2 V naught more than V1. So that is something that we know beforehand. We keep that in mind. The same as this analysis. But also we can see that if you take a general element here, a current element IDL like this, here this is y equal to y. So the magnetic field is a function of y. Okay. Now the corresponding element on this side, this is also at the same y coordinate. So it is at having the same magnetic field Vy. So what will happen? The force acting on this, which is inwards, this force and this force will cancel each other. So that is why the net horizontal force will be 0. Just write this more properly. So this force element acting on this VL and this force element acting on this IDL, okay, they cancel each other. So horizontal component or Fx becomes 0 by magnetic field. But as you can see, the force acting on this, which is let's say F1, does not balance the force acting on this, which is F2. So the net force because of magnetic effect, we can say it's like this. That one's y component becomes F2 minus F1, which is IL V2 minus IL V1. And from here we've understood. So this is 2 times IL V0. This is the effective y component of magnetic force. So now coming back to the FBD of the loop, you understand that there is some net magnetic force acting like this, which is 2 times IL V0 and mg. So this will give us the expression. G minus magnetic force divided by mass. So G minus 2 times IL V0 divided by mass. And then we just substitute the value of I, which we got in terms of this, the velocity V, instantaneous velocity V downwards. So we get the acceleration as G minus 2 by 3 B square by M lambda current. So this kind of term. So this is the acceleration as a function of V. Okay. Whereas the current as a function of V was V naught V by 3. And then you can easily see terminal velocity condition. Acceleration will be 0 at V equal to terminal velocity. So terminal velocity will just become 3 by 2 times mg lambda by V naught square. Okay, people, so hope all the parts of this question are clear. Let me just so we come to this current over here in this section, and then in the section below Pupils, hope this is clear. I is missing in the denominator. L. Will there be an L in the denominator? Yes. Sorry. So there will be an L here also. No? There will be an L here. Let's move. So B naught L by M is multiplied by 2I. So that becomes. So there will be LV here. And so there will be. Okay. Now it's all right. Basket. Okay, good. Now there is an interesting, trickier variation of this question, which I will give as a question to you and you try out in your free time, because I want to move on to other parts also now. Okay. So that question is something like this. So you can do this as a homework kind of exercise yourself. So just remember to refer to the whiteboard notes later and do this question yourself. So in that question, what is happening is this is a rough surface and this is a hollow metallic cylindrical shell. So now this is in a region where there is non-uniform magnetic field, which is like this. Just give me a second, guys. My software is playing up. Just a moment. I'll reshare the program. I just need to restart my whiteboard software. Okay. So this is in a region where there is again that kind of non-uniform magnetic field. Increasing linearly with the x coordinate, but going into the plane. So there is a non-uniform magnetic field given by this relation. Minus k cap going into the plane this time because x and y is like this plane. So the hollow metallic shell is actually in 3D, it is like this. So the shell has radius r, okay, length like this L, okay, and very small thickness d. Okay. So this thickness over here, this one, that is d, very small, and it's the metal has resistivity, okay, and also the shell has mass m. The whole shell has mass m. Okay. So this is the property of the metallic shell. Now the shell is initially at rest, and then what we start doing is applying a constant horizontal force. An external agent starts applying a constant horizontal force whose line of action passes through the center of mass. Okay. So the constant horizontal force F that starts acting such that it acts through the center of mass. So the shell was at rest initially when a constant horizontal force F whose line of action is through center of mass C starts acting. So we again have to find the induced current I and acceleration as functions of instantaneous speed V, assuming the shell rolls without slipping on the ground. Okay. And we have to also find the speed as a function of time. Okay. Assuming no slipping. Okay, so this is a question I want you to take your time and do over a period of maybe 2-3 days. Think it through carefully. Various options of how you will solve it. And you can get back to me about it, I will discuss with you. Because currently I want to move on to some other type of questions also. Okay, so hope the situation of the question is clear. This will be in the notes, so you can just pick up the question and try it out yourself. Okay, now moving on, let's come to something that Bhaskar has requested for, and that is dipole in a non-uniform electric field. So we start with an example where the electric field is along the x-axis and the dipole moment is also along the x-axis. Okay. So suppose we have something like this, but it's a variable electric field. Okay. So Ex is a function of x. Let's take that time. Okay. So the typical example would be something like this. Let's say I have an infinite line of charge. Okay, which is lying along the y-axis. So infinite line of charge on the y-axis. Okay. And now on the x-axis, I have kept a dipole. Kept a dipole like this, such that the center of the dipole at a distance E, and the dipole length is 2n, and the charges are plus q and minus q, and L is very small compared to E. So you want to find the interaction between them, what is happening. Okay, is there force, is there torque, and what kind of force or torque is. Okay. So interaction, force, torque on the dipole due to the line. Okay. So this is a case where you can see that basically what is happening is this, that the dipole is along your x-axis, and the electric field in that region, at that point where the dipole is present, that is also along the x-axis. But this electric field is some kind of function of x along the x-axis. So whenever this happens, the method we use is like this, that if this is x equal to x, then this is x equal to x plus L, which we can treat as a x plus delta x, where delta x is small compared to x. Okay? And this is at x equal to x minus L, or x minus delta x. So the force that this guy will be experiencing and the force that this guy will be experiencing will not be same. So the net force that the dipole is experiencing, the net force will become the force on the positive charge minus the force on the negative charge along the x-axis. We're taking this as our x-axis. So this is the effective situation when something like this is happening. Because we have electric field in this region, which is like this. Ex is a function of x, that kind of thing. Okay. So, इसको solve करने के लिए अभी the trick that we use is that this net force becomes q into E at x plus delta x, okay, minus q into E at x minus delta x into I. Okay. So you can see that it becomes q into E at x plus delta x minus E at x minus delta x. Like that. So since delta x itself is small, therefore E at x plus delta x minus E at x minus delta x and is nothing but a change in E, okay, which is nothing but the rate of change of E with respect to x, or we can just write this as, at the moment we can write this as delta E by delta x times 2 delta x, because the difference in the coordinate is 2 delta x. Okay. So that is nothing but dE by dx into 2 times L, where L is the half length of the dipole, 2L is the size of the dipole. So this becomes my delta E, which I'll replace as this. Okay. So the force you can see is becoming Q into dE by dx into 2L times I. So you can see that this is actually becoming P into dE by dx. Okay. So this becomes the net force when this situation happens. Okay. When the dipole is also along the x-axis, the electric field is also along the x-axis, and E is some kind of function of x. So this is the shortcut method that we can directly use when this is happening. So I'm just going to leave you to go through this method once and then apply it directly to the example I've given you above. Okay, so I'll come back to the example above, but first just go through this method. So the dipole center is at the x coordinate x. So the positive charge is at x plus L, which we can treat as x plus delta x. And the negative charge is at x minus delta x or x minus L. Because L is very small in comparison. The size of the dipole is negligible, small. So that's the logic of these terms here. So now you can see the force acting on the positive charge and the negative charge. Okay, so finally, we come up with a formula like this. Okay, so now just apply this to the condition, the situation I told you about. You have an infinite line of charge along the y-axis of lambda, and you have the tiny dipole moment p, which is kept on the x-axis at a point x equal to e, and its orientation is also along the x-axis. Okay, so apply this situation now to, for example, this question, and see what formula you can come up with directly without doing such a lengthy approximation and all this. Okay, so people trust you would have got this. So here you can see that at any point on the x-axis, the electric field due to the line, infinite line, would be how much? It would be lambda by 2 pi epsilon naught x I cap. So if you put the dipole along the x-axis, okay, at x equal to a, like this. So the orientation of the dipole is along the x-axis and it's placed at this position. Then dE by dx at that position will become minus lambda upon 2 pi epsilon naught e square, okay, at x equal to e. So the force acting on the dipole will be along the negative x-axis because your dE by dx is coming out to be a negative quantity. So it will become minus of lambda into q into 2l upon 2 pi epsilon naught e square. This will be the net force acting on the dipole. Or you can write it as minus lambda p upon 2 pi epsilon naught e square. So this is how we make use of that direct formula at the exam level. Otherwise, you would have to sit and first, write the force on the positive charge, negative charge, then subtract the two forces, then apply the condition that the L is very small compared to A. Okay, so then this approximation thing would come in by binomial approximation actually. So it would become very lengthy. It would basically become the derivation of this formula that we want, dE by dx into P. Okay. So people hope this is clear. Now let's move on from this to a two-dimensional example, and then you'll see how to modify this formula when there is two components of force involved. Okay. So we have a situation where in the two-dimensional plane, so in my xy plane, I have some, let's say, variable kind of electric field. So see, my electric field lines are something like this. And then I have kept a dipole somewhere like this. So I have a dipole like this. So I have electric field which is two-dimensional, and the dipole moment which is also two-dimensional. Okay. And Ex and Ey are non-uniform quantities. Correct. So they are functions of x and y, like that. Okay. So how will we calculate the net force? So for example, there could be a point charge located at the origin. So it's creating that radially symmetric field, and you just kept the dipole somewhere, in the xy plane at some random kind of orientation. So that's an example. So how we deal with this is something like this. See, मेरा dipole moment अगर ऐसा है, so my positive charge is sitting here, my negative charge is sitting here. Okay. And this length is 2n plus qn minus q. And in general, I have that kind of electric field. So this point's coordinates are some x comma y. Okay. So what is the coordinate of the positive charge? The positive charge is located at x plus some delta x and y plus delta y, where delta x is your L cos theta kind of term and delta y is your L sin theta kind of term, where that theta is tan inverse of y component divided by x component of your dipole moment vector, because your dipole moment vector is like this. Right? So if this is at an angle theta, the x-axis, so this angle here, so theta with respect to your x-axis and your y-axis. Okay. So that is your positive charges location, and your negative charges location similarly is at x minus delta x and y minus delta y, where delta x and delta y have the same meaning. Exactly same. Now electric field has both components now. So this is experiencing some force along the positive direction because of the positive component of electric field. So this is Q E at y plus delta y, and this is Q E at x plus delta x. And similarly, this is experiencing Q E at x minus delta x. This is experiencing Q into E at y minus delta y. So you see what the net force on the dipole is now becoming. F net is becoming Q into E at x plus delta x minus E at x minus delta x I cap plus Q into E at y plus delta y minus E at y minus delta y. Okay. So this is becoming Q into del Ex by del x into 2 times delta x I cap plus Q into del Ey by del y. Because remember here that Ex and Ey are both functions of x and y. So that's why we have to use the partial gradient notation. 2 times delta y. So this is Q into del Ex by del x. Now this was basically the size of the dipole's x component. Okay. So this is 2L cos theta I cap, and similarly this is 2L sin theta j cap, where we've understood earlier what your theta is. Okay, so further when you take the Q inside, this becomes 2 times QL cos theta is nothing but the dipole moment's x component. Okay. And this becomes Q into, sorry, it becomes del E by del y. Sorry, del Ey by del y. Okay. Into 2 times QL sin theta, which is nothing but the dipole moment's y component. Okay. No, we're not assuming 2 dipoles. We're just assuming some electric field which has x and y component. So electric field can be the field because of a single point charge kept at the origin, or it can be the field because of a line of charge or anything. Then we'll see 2 dipoles. Okay. Dipole is kept like this, beta. dipole is kept like this. Okay. So effectively, yes, it becomes, it has, so this angle is theta. So that is what your 2ql cos theta is. So this is nothing but this term into dipole moments x component plus this term into dipole moments y component. J. Okay. So this becomes our net force when this situation happens. So this becomes our net force when a dipole such that its dipole moment expressed in component form is this, is placed in an electric field E, which is Ex I cap plus Ey j cap, okay, where Ex and Ey are some sort of functions of x and y. There's some other function f2 of x and y. So when this dipole is placed inside this kind of a field, it experiences a force given by this term. And this automatically reduces to our earlier case if there's a one-dimensional field and the dipole is placed in that one-dimensional field. Or, even if you make one of these two one-dimensional, the question will still reduce, the formula will still reduce to one-dimensional term. So I'll show you an example, and then we'll come to the dipole-dipole interaction also. Okay, so that's a little bit different, because there we'll use the r cap and theta cap this thing, because electric field of a dipole you always express in terms of radial or polar coordinate system instead of Cartesian coordinate system. Okay. So imagine this situation above. The dipole is randomly oriented in the xy plane somewhere, and in that xy plane I have variable electric field such that at every point there is some x component of field and some y component of field, and that Ex and Ey themselves are variable quantities. They are varying with x and y, or they are non-uniform quantities. So this is the two-dimensional case. So Bhaskar, what you are saying that instead of assuming we have two dipoles, you are just saying that you have one dipole only, but it has two components. And the dipole moment P can be written as the sum of two components. No? So it's effectively, yeah, like as if it's a combination of two dipoles, one along the x-axis and one along the y-axis. Okay, so understood this concept, So now next we have to just apply that in this diagram. So you see there are two components of force acting on each particle, and those components correspond to the value of Ex and Ey at that point. So जो positive charge particle है उसका position क्या है, x plus delta x and y plus delta y. And similarly for the negative charge particle, then your net force on the dipole becomes like this. Of course, along with this there will also be a torque. In this case, along with the net force there will also be a torque, which you can approximate as P cross E. Okay, so hope the final formula is clear. So let's start with an example application of this. Then we'll come to the two dipole interaction also. That's a different situation because we use polar system over there. The concept is the same there also, but we use polar coordinate system there. So in my next example, I have, let's say, an XY plane. And what I've done is I've placed a charged particle Q naught at the origin. And then what I've done is I've placed a dipole somewhere here like this. So this is a positive charge and a negative charge. Plus Q and minus Q kept at a distance of 2L like this. And this is placed at a position vector, or let me just say the coordinates of the center of the dipole. Center of the dipole have coordinates, let's say 3R, 4R, where R is very large compared to L. Okay, so something like this. So you have to find the net force and torque on the dipole due to the particle. So though the particle creates a three-dimensional field, but here the dipole is lying in that two-dimensional XY plane, in which at every point the field has an XY component only. Okay. So just see how you can apply the concept over here. Okay, cool. Okay, so here a charge particle is at the origin. So at any point xy, position vector xi cap plus yj cap, the field is eq naught by r square r cap. So it is eq naught upon x square plus y square to the power 3 by 2 into xi cap plus yj cap. Okay. So you can see that the x component of the field is eq naught x upon x square plus y square to the power 3 by 2. And the y component of the field is eq naught y upon x square plus y square to the power 3 by 2. So a dipole placed somewhere over there. So now luckily I'll just need one term, but anyway, in general, a dipole placed having components like this will experience a net force such that the x component of the force is this and the y component of the force okay, so this will become the general formula of the force. So you can see that here Ex is eq naught x upon x square plus y square to the power 3 by 2. So its partial derivative with respect to x will become how much? Kq naught. Now we will have denominator into derivative of numerator minus numerator into derivative of denominator. Whole thing divided by denominator squared. So this will become Kq naught. We can take x square plus y square to the power half common in the numerator. This will be x square plus y square minus of 3x square. Something like this. And if we needed the other term also, it would just come by symmetry. In this particular case, we have kept our dipole as just pi cap, but at the position x comma y, which is 3r comma 4r. Okay. So the force acting on the dipole will just become p into del ex by ex I cap, because according to this, what is happening? My x component of the dipole is p and the y component of the dipole is 0. So it will experience a force which will be only along the x-axis, and that will be okay. So this will become 16 minus 18. So minus 2 times r square divided by 5 r ka whole square to the power 5 by 2. This will be the net force. Okay. Whereas torque you can do more easily by just using cross product. For torque, you can just use the concept that at that particular point, the field is along this sort of direction and the dipole is kept like this. So it will experience a torque like this. E sine theta. In this case, K cap coming out of the field. And that angle and all is easy to calculate. Sine theta. Is the concept clear, people? Let's go over this whole thing. So we have a charged particle at the origin. So at any general point on the xy plane, field का formula ऐसा हो जाएगा. So this is the x component, this is the y component. So to calculate the force on a general dipole placed like this, you need these two terms. You need del Ex by del x and you need del Ey by del y. So here the dipole is only along the x-axis. So we just need one term, del Ex by del x. Okay. So that will become, you are partially differentiating this fraction. So you use this thing rule, the quotient rule of differentiation. Okay. So denominator into differential of numerator minus numerator, which is x, into differential of this term. That is 3 by 2, this term to the power half into its derivative. So 2x divided by the denominator square. The rest is all just algebraic manipulation. So also visually you can understand that that positively charged particle and that negatively charged particle, because of this particle here, this will experience a force like this. This will experience a kind of force like this. So the net force is effectively becoming along the negative x-axis because this is a longer force vector compared to this. Now just imagine that this side of this triangle is actually very small compared to this. It's a very thin triangle. So effectively the force will be towards the negative x-axis, which is what this will show finally. Okay, so you can eliminate further and all. I mean, I'm not completing the calculation, but you got the idea. Now we come to the case of the interaction of the two dipoles. So you do the same kind of thing there, but using the this thing, the radial or the polar coordinate system. So if I, let's say, have one dipole which is placed over here, and now let's start with an easier case where the second dipole that I'm placing is, let's say, along the radial direction. So it's at a distance, at a position vector r, where this angle is some theta, and my second dipole is now placed like this. It's directly placed radially. This is P2, and this one here is P1. And effectively, this position vector is R. So यहाँ पे क्या करेंगे? We'll understand that we want to find the net force on P2 because of P1. So let's say that's what we want to do. We want to find the net force on PT due to P1. Okay, so we will make a sort of extended free body diagram of that dipole P2, how it is getting affected by the field of P1. So suppose P2 is like this. So it has a positively charged particle here and a negatively charged particle here. Now compared to this dipole, the one which is over here, the field of the first one, this is field of P1 at the position vector R or R theta, that is given by that formula K into 2p cos theta divided by R cube, R cap, plus p sin theta divided by R cube, theta cap. Okay. So this will experience some radial force, and this will experience some tangential force, and this will experience some radial force, you can call F prime, and this will experience some tangential force, because this is now your theta cap's direction, and this is your R cap's direction. Alright, so this is clear. So your net force will be Fr minus Fr prime R cap plus F theta minus F theta prime theta cap. Okay. So again, this term, you can simplify it and write it now like this, that this is Q into radial component of field at R plus, let's say, L2, okay, minus radial component of field at R equal to R minus L2 into R cap plus, and this was that charge Q2 into tangential component of field at R equal to R plus L2 minus tangential component of field at R minus L2. Okay, because what is happening is, देखो, जो second dipole है उसके charges plus Q2 and minus Q2 है, और उसका effective length L2 है, I mean 2L2 है. So ये जो उसका center point है, इसके coordinates R theta है. So therefore plus Q2 is at R equal to R plus L2, and minus Q2 is at R equal to R minus L2. The center point of that dipole is at the position vector R. So the actual charges are at a distance more than R along the radial direction and at a distance less than R along the radial direction. So that is why at the position of Q2, the field it is experiencing is the radial component of field at r plus L2 and the tangential component of field at r minus L2. And at the negative charges position, that is f prime and f prime over here, the field it is experiencing is the radial component at this position and the tangential component at this position. Okay. So people, I'm going to reboot and restart this whiteboard software once. Just give me a second. But you've got an idea what we are going to do next. We're going to again use the partial gradient concept. Right. So अभी क्या करेंगे यहाँ पे ये वाला term again we will write in terms of partial gradient. So this net force will become Q2 into del ER by del R times 2L2 R cap plus Q2 into gradient of the tangential component, but with respect to R, because it's the R position which is changing, into 2L2. Okay. So you can see that this will become Q2 into 2L2 will become P2 into del ER by del R cap plus again P2 only, but into del E's tangential component by del R. Now you substitute the values. So radial component of field because of the first one was Kp1 cos theta by R. So minus 3 Kp1 cos theta by R to the power 4. Right? And tangential component was Kp1 sin theta. Twice of that by, oh sorry, this one was twice. This one is just, so there will be an extra 2 term here. So will become minus 6. And this one is just this. Okay. So now when you substitute that over there, you can see that you get the force as P2 into this term. So minus 6 Kp1 cos theta by R to the power 4 R cap plus P2 into minus 3 Kp1 sin theta by R to the power 4. So this is becoming actually something like this. That is, if you take 3P2 common, in fact, take 3P2 by R common, you are left with 2Kp1 cos theta so you are just left with the electric field due to this one. Represent like this. Okay, so I'm just going to leave you to this. And for the torque, you can see, again, you can use the same method. It is electric field, sorry, it's the second dipole moment, cross product with the electric field. Due to the first one. So this will actually become P2 into this one's tangential component, because the radial component is along P2 only, because P2 is along r cap. So r cap cross r cap will become 0, and r cap cross theta cap will give you something coming out of the plane. So this will be coming out of the plane, or basically that axial unit vector. Okay guys, so hope the method and everything is clear here. Okay. So this is a bit lengthy and complicated. So, generally this has not been observed in JEE yet, this kind of analysis. But that kind of question I showed you earlier, where you have infinite line of charge and a dipole just placed somewhere on the x-axis like that. That kind of thing is the more common type of question at JEE advanced level, which is easier version of this question because there's only one dimensional situation to solve. Okay. Or if you place the two dipoles along the same axis, then this becomes easier. You can just, if it's for example, it's only the r cap axis, the theta cap term is not there. Okay, so you can just replace r with x and r cap with I cap and reduce this whole problem. Theta will be 0, so this sine theta term will become 0, this cos theta term will be the axial point on one dipole. You place another dipole coaxially with it, so that becomes the easier one-dimensional version. So you get that P1, P2 upon x to the power 4 type of term, which you can see over here. This term will not be there. Cos theta will be 1 and r will be x. So that kind of. Alright people, so that brings us to the end of today's session. I just saw that there were some questions that you people, Omkar and Chikshu, etc. had sent on the group. I didn't get a chance to see it before the lecture. I had another one. So I'll go through the questions and send you some hints and solutions. And if something is extra complicated, we'll discuss in the next lecture about that question. Okay. Plus, there are some additional modern physics questions and all I wanted to discuss. So we'll keep that for the next lecture. Okay. So hope this lecture was effective for you people, and all the best and stay safe and continue with your good studies and everything. Okay. That's it from me. Bye and thanks. Okay, Omkar, thanks. Okay, Chakshu, Bhaskar, all of you. Ananya.